Greetings viewers, in this video we will attempt Cambridge A-Level Further Mathematics Component 3, which is Further Mechanics. This is variant 1 from May June 2025 series. We'll attempt question 7 now. Previous questions have been uploaded to the playlist. So it's giving us this diagram of part of a circle, and it's a fixed hollow sphere with a radius A and center O. The points A, B, C lie on the inner surface of the sphere with OA and BC horizontal. Alright, so that's a horizontal line. A portion of the sphere has been removed, so this is no longer there, and the vertical distance Ka above the center of the sphere. Alright, so ABC, OABC lie on the same plane, vertical plane, and OB makes an angle theta with the upward vertical O. A particle of P with a mass m is free to move on the smooth inner surface. So we ignore friction here. And the particle P is projected vertically downward. So it's given, so there is an initial speed. It does not start at rest. So and the initial speed is u, which they are given us this expression. And the reaction on P at B, so here is half the reaction on P at A. So we want to find the value of K, or basically the constant of the height here. So let's take a look at the free body diagram on both of these parts. Right? At A, right, how does the free body diagram look? I'll just sketch this. So that's the string, I suppose, or not string, but the direction of the center. And it's like directly like that. Okay, so at this point, it's at the center of a circle, so it's going, I assume it's going directly down. So what forces do we have is gravitational force, weight, the normal force or reaction force at A, and also we'll have the resultant force because it's in a circular motion. There will be a resultant force going to the center, which is the centripetal force. So at A, let's do the force balance. So I think, yeah, in this case, we only need to do the force balance in terms of the horizontal direction, because I mean the vertical direction, what you want to do, even if you have the resultant force is as a ma, the second law, so you only can get the acceleration a is the gravity, so there's not much useful information for us, so we just go for the horizontal direction in this case, and that will be equal to the resultant force of the centripetal force. So that MAC are right here first. AC, if you forget, there is a formula, yeah, the uniform circular motion, the acceleration of the centripetal acceleration is this expression, v squared over r. Or in this case, at the initial point at A, v is u, so we'll use that. mu squared divided by r. Radius, again, that's a. So we just use a here. What forces do we have in the horizontal direction? We only have the normal force. So that's just NA. And we'll just write the axis here, declare our axis, so that's positive and that's positive. So that's at A. Now at B, it's a bit trickier. Here, the particle here, and then this is the center of a circle. First, we have the weight, or mg, at this point. And remember, normal force, because the wall something is like if there is a wall, it looks something like that. So remember, normal force always acts perpendicular to the surface of the object. So it will be going in the same direction as the centripetal force. So normal force will act towards the center also. So NB here. And of course, you will have, again, the normal force, or it's the resultant force, sorry, it's acting towards the center again. This is centripetal force. There's not much use of information to do the vertical direction. So we're just going to do the horizontal direction, and we can declare our axis like this. So it makes our life more convenient, and we can resolve this weight force. So if we resolve it like that, and like that, this is a vertical, and then this is the angle theta. Okay, as labeled in the diagram. And yeah, so means this part instead is theta instead of the just now the one. Right, so this is theta, and we do the force balance in the horizontal direction or the x direction as we declared. Again, is equal to the MAC. That's the resultant force. And the AC in this case is still the centripetal acceleration, v squared over r. But in this case, it's v at b. So let's say the particle is here, and you will have a speed of vb at this point. So we're gonna use vb squared divided by r is still a. It's still the same circle. And yeah, the forces you're gonna have nb going in the correct direction, and also mg cosine of theta also going in the same direction. So it's both positive here. Let's isolate nb so that we can do the simplification later on. Okay, so this is the the Newton's second law, everything. And we are also given this piece of information. Normal force at B is the half of the normal force at A. So NB equals to half of NA. And we can use these two and form the equation from there. After you do this equation, I'm going to use again what they've given us. U is this expression. So u squared will be just get rid of the square root, and I can substitute this inside this equation here, and I also can cancel out all the masses, right? Because on both equation they are the same. I mean on both sides of the equation they exist. So also let's solve for this cosine theta. Okay, we know the hypotenuse here is A and the adjacent to this angle is KA. So cosine theta, that will be KA over A, and just leave us with K to get rid of the cosine theta, yeah. Then we can isolate VB squared as our left hand side. In this equation, we have too many unknowns, and we cannot solve. VB, A, and K, they are all unknowns. Yeah, so we want to find some way to cancel that out, and we're going to use the conservation of energy. This states that in the closed system, the change of energy, the total change of energy is 0. So we're going to have to evaluate the initial and final energy. At the initial point, there is a kinetic energy there because it's being projected from a speed u, and not at rest. So there is a speed, so there is a kinetic energy. And there's half mu squared, and u is given us in this expression, and you can just directly substitute that in. So that's our initial expression of kinetic energy, and as written here, we set the datum at this point, so there will be, at the datum there is no, or we declare at this point the gravitational potential energy is 0. So from here then any change of potential energy or gravitational potential energy will be caused by a change of height from this datum point. So our final energy, we have kinetic energy first of all, so it's half mvb squared. So at this point it has a speed of vb, yeah, at this point. And vb already, just now we have the expression, right? That's why we isolated vb squared. And then we also have the change of the gravitational potential energy, which is mg delta h. Delta h in this case is a ka, that's the vertical height from a to b. So we're going to go ahead and equate the total energy initially and the total energy at the final point. And from here, it's just a matter of solving for k, because m, g, and a, it all cancels out, right? So we get rid of the unknown a and also m. So we're just left with one unknown, which is k, which is what we want to find. And you should be able to get k is 0.2. And I think k is dimensionless, right? It's just a constant. So yeah, this is to find k. Now part B, find the expression for u in terms of a and g in the case that the particle just reaches b. So when it just reaches b means at this point the speed will be 0. So it uses up all the energy, and at this point it gains. I mean, the kinetic energy loses and gains to become the gravitational potential energy. So again, we ignore friction, any work done by friction. So at when it just reaches B, VB will be 0. Oh yeah, yeah. Okay, VB equals 0 means the potential energy at the final point. Sorry, the EK or kinetic energy at the final point will be 0. All the kinetic energy from the initial converted fully to the potential energy at the end. And the initial will have as half mu squared. Final one, we're going to get mgka. So we use this and isolate u. And k we have found before, right? That's just 0.2. So 0.2, you multiply in, you can get 0.4 G8. Part C sort of transformed itself into kind of kinematic projectile motion question because they want to find the expression of U where the particle passes through B and then reaches back to C. So that means is they want us to find the starting speed for which is projected downwards where it reached B already and then it's projected out at B again, so it's projected up at some angle and then somehow it uh it goes to a projectile motion and reaches back to C. Need to figure this out I need to figure this out slowly. So first probably is we want to find what's the speed here, VB, that it makes it possible to reach back to C. And for that we're going to apply these kinematic equations. We're going to use this one because the displacement we can kind of figure it out from this circle, from geometry, right? Sy obviously that's going to be 0 already. The displacement in the vertical direction because it lands at the same on the same level from which it is projected. But the sx or the horizontal displacement, there is something to find. That is can be using the trigonometry. CB, that's the sx, right? BC or CB. And then you can use trigonometry, this right angle triangle, this half of CB is the opposite of the angle, so you can use the A sine theta for this. So the SX will be, or BC will be 2 sine theta, 2A sine theta. So let me just write it down there also. So SY is 0 and SX 2A sine theta. So I think yeah, we can just leave it like that first. And yeah, let's go and apply the kinematic equation. So first we're going to figure out for y in the y direction. 0 will be uyt plus half ayt squared. And ay, remember, is gravitational force going downwards, and we'll take it as a negative 10. So ay is a negative 10 meters per second squared and not 9.81. So factor it out here. Or maybe I also can rewrite uy, that is our vb resolved in the y direction. So how do we find that also? We need to come back up here and resolve the vectors. So we can resolve like that and then upwards also. So given theta is this one, here also will be theta. And VBY, that's the vertical one, it will be sine theta. VB sine theta. And I'll replace that here, VB sine theta multiplied T. Then we have a negative 5. Then both terms you can factor out the T. You're left with just, or maybe I should not, yeah, I should not, this AY, okay, this I should not put as 10 because they want it in terms of G. So I put as negative G. So here I'll replace it with G. So T either is equal to 0 or it will be equal to VB sine theta over G. Half G. Half G here. 2 VB sine theta over G. Alright, so that is the first equation. Now we can deal with the x direction. We also have the same equation, Sx equals to u, or Vbx in this case, t plus half ax t squared. So we don't consider air resistance, so this term goes to 0. And Vbx, so we already use sine for the vertical, so the horizontal will be cosine. Vb cosine theta, and t then equals to 2a sine theta. So this t already we have found previously from the y direction. It's this expression. So we also can go ahead and replace it into here. I can isolate this Vb squared. And because cosine already we have proven it here just now, right? We have cosine theta, we've proven it to be k. So we can just write ag divided by k. That's our Vb squared. Okay, so far that's it. We have a Vb squared, but we want to find u, right? So we're going to go backwards some more. Yeah, we're going to go backwards some more using this conservation of energy equation again. We know that the initial kinetic energy, and we set as datum, so there's no potential energy, equals to the final, or initial means at A, initial means at A. So now we cannot write initial final because there is an intermediate point at B. So this is just now we have found the speed at B. This is the speed at B for which the particle needs to have to reach C. So now we're going to substitute this back into just now the equation. So EKA, if you recall, that's half mu squared. EKB, that's half mvb squared. That's the kinetic energy at B. And the change of potential energy, mg delta H. Delta H is AK, okay, from just now. VB squared, I will just substitute what we have again. We have gotten this expression for VB squared. So I will substitute this into here, this VB squared. And then also, all the terms contain the mass. So I can just go ahead and cancel that also. Okay, so far we got until here. Okay, k is a value, k we have found just now to be, what was it, 0.2, right? So k, yeah, we can just simplify that value there. It's just a matter of simplifying and then finding u isolating by itself. And you should be able to get this final answer for u. And yeah, and so in terms of a and g, right? So yeah, a and g here, and k, yeah, we simplify it. So this should be the final expression. So thank you for watching.